All right. Hello, everyone, and welcome to Handmade Hero, the show where we code a complete game live on Twitch. No engine, no libraries, because you know what? It's old school day up in here all the time. You know what I'm saying? Like, we kick it old school. None of the crazy rap musics and heavy metals that the kids are listening to today with their, ridiculous hair and their other things. It's just like that's not that's not how we roll. We don't try to put on rollerblades and go like crisscross through the cones or the other things that the people are doing in California. That's just not how we are here. This is old school traditional programmer values here on Handmade Hero. And so, with that said, off we go. If you have pre-ordered the game and want to follow along with the source code, you can go ahead and check out that link that you should have gotten in your email. And today is day 89, so you're going to want to unpack day 88 source code. That's what you're going to want to do, because that's where I am at. And so, do that so that you and I will be aligned. We will be working on the same code, because otherwise we will be divergent. And despite the fact that that appears to be some kind of an awful young adult novel that is currently not sweeping the nation because it probably wasn't very good, I feel like we should avoid that in terms of our code base. All right, so let's take a look at what happened on Friday, because some stuff happened on Friday and it kind of changed everything around a little bit. So what happened on Friday is I just kind of finally got sick of not having a renderer, and so we just started pulling things out into, for lack of a better term, a renderer. And honestly, I kind of felt like it was the right thing to do, because once I started doing it, I was like, yes, we should probably be doing this. So I think what's probably going to happen here is either we're just going to go ahead and write the renderer this week and next week, or however long it takes, probably longer than that if we write the whole renderer. So we'll take a couple of weeks and write the renderer, or we'll at least take a week and write enough of the renderer to make it not be bothering me anymore. So yeah, maybe we don't write the whole renderer, but we write enough, if that makes sense. I don't know which one we'll do. It remains to be seen. Maybe we get up a good head of steam, we'll just write the whole thing. But I think at this point, it was getting annoying enough that I just decided to make the call. Because we've just got a bunch of crufty code in there that was sitting around doing ugly stuff because we didn't have a renderer. And at some point, you just kind of have to say, let's do that. And similarly, we had another thing that we might consider to be a blocking factor, which is that in our ground rendering code, which we had kind of started to want to make into more of a thing so we could have multiple ground levels and stuff, that was kind of the next big milestone that we wanted to kind of hit. We run into the problem that we don't have scaling at all, right? Because we don't have a renderer. And so how are we going to test out rendering of our ground pieces if we can't scale them? Because maybe we want sort of lower levels on the screen to be shrunk, right? So that they look like they're further away or something like that. And we want them to kind of be able to do that smoothly as we go up and down stairs or other things like this. If that's the case, then we need some way, even if it's not a very good renderer or it's not a very fast renderer, we at least need something, right? In order to test that and get a feeling for whether or not it's going to be workable for what we need to do, right? So I think that's where I'm at. And so I think I'm just going to go with it until we hit something that suggests that we need to do something differently. So let's talk briefly on the blackboard about what's going to happen here, just so everyone's on the same page. And just at the head of the week here, we can kind of get a little bit of a kind of an overview. It is day 89. Yes, it is. So what I want to be able to do with this renderer is I want to be able to have the game code, right? I want to be able to have the game code issue a bunch of essentially instructions that are going to tell the renderer what to do, but I don't want them to actually be executed right away, okay? In other words, I want the game to be able to issue instructions. So when we're coming through here and it wants to render things, every time it wants to render things, what I want to do is I want to put it into a buffer. Okay, so I want to put it into a buffer here where it says like, okay, render the head of the thing and then render, this particles or something, right, that are here. I want to basically build up a list of things for the renderer to do, and I called this a push buffer. And the reason that I called it a push buffer is just because you keep pushing things onto it. It doesn't like shrink or anything ever, right? It just, you keep pushing onto it and onto it and onto it, and eventually the renderer actually renders the whole thing and then discards it entirely, right? That's just how it works. So why do I want to do that? Well, there's a couple different reasons I wanted to do that, and I'll briefly say what they are. The first reason, and probably the most important one, is that I want to be able to sort, okay? So I want sorting in here. Because what I want to be able to do is I want to be able to take all the things that we're going to get rendered, and I want to be able to think about them in terms of what order I want to do them in. And in order to do that, I need to see them all. Now, I could try to structure the game so that it went through and actually did everything that it needed to do in the order in which it had to be rendered, right? We could do that. But that imposes a lot of constraints on the game, and it makes the game do a lot of thinking that I don't really want the game to have to do. I would like the game routines to be structured so that they're about making it fast and flexible for us to do interesting things, and so that they're optimized for doing a lot of off-screen calculations as well, like I was saying. And so what I don't want to do is build the whole game architecture just around how you're going to render it. Now, that may sound like a weird thing to do, not the what I'm suggesting, but the thing I'm suggesting against. That may sound like a weird thing to do to ever build the game entirely around a renderer, but that wasn't that unusual in the old days, because when system resources were severely constrained, think Atari 2600, ColecoVision, Commodore 64, in those days it may have been the case that you literally could not make the game work if you ever wanted to do something like queue up a bunch of render commands and then execute them, right? That's simply nonsensical, because you did not have the kind of system resources it would take to do that efficiently. Your game would run awful, it wouldn't have enough memory to run, it would be too slow, you know, who knows what would happen, but that simply wasn't on the table. Nowadays, we have the luxury of having just this incredible amount of horsepower under the hood. And so what we can do is we can make different trade-offs there. Now, I don't advocate making the trade-off of, let's just write a bunch of crappy code and use all the CPU to allow us to run crappy code. You know, I advocate against that very strongly, because I'm tired of running really lousy software on machines all the time, which is typically what people tend to be shipping these days. So I don't advocate that, but what I do advocate doing is trying to figure out where you can make those trade-offs for the betterment of the game code as a whole, right? And this is one place that we can do that, because there's a bunch of things we can get if we do this, if we allow this sorting. First of all, we allow the game code to be structured in a more efficient fashion, and it doesn't need to have that sorting logic baked into how we structure things. So all of the stuff in the game can get more efficient and more flexible because of that, so that's a plus. And the other thing that's a plus is it means that we can sort things essentially on, if you will, we can sort things differently depending on the circumstance. And so let me explain a little bit what that means, right? So let's say we then want to take this push buffer and do the rendering. And so this comes to the next big benefit here, which is the output target, right? So the output target is where this push buffer is actually going to go eventually, right? So OpenGL is one place it could go, right? Direct 3D is another place it could go, right? Mantle is another place it could go. Like, I'm trying to think if there's anything else really. Software APIs. I don't think so. You could imagine some console API here, like a you know, whatever the Xbone or the PS4 is doing or something like that. And then finally our software renderer, right? That we write. Okay? And this software renderer, there might be different versions of this, right? You could imagine maybe there's an SSE2 version, that's what we do now. Maybe there's an AVX version, maybe there's an AVX2 version, maybe there's a Neon version for ARM-based processors. So there might be different software renderers. And so one of the things that this push buffer does allow us to do is the sorting, you can almost think of more as processing, right? So don't think of it just as sorting. Think of it as any kind of processing you might want to do. It allows us to translate this push buffer into the most efficient thing for the target without having to rewrite all the game code, right? So it does provide a way for us to get a layer of portability that makes it possible for us to optimize for a lot of renderers, render targets, without us actually having to rewrite the game. And while again that's something that sort of sounds a little bit like, well, isn't that kind of cheesy? Like, don't we want to try and make things optimally efficient? Again, there is this concept of what will you actually end up doing, right? You know, if you go to the extreme of sort of the we want to make everything efficient philosophy, it's kind of untenable. Just like the extreme that we're at right now today in most software, where you don't care about performance at all, and you're just like, I don't care, I don't even think about it, I don't even know how memory works, it's a mystery. I get back these reference counted things and I don't even know where they come from, right? Just like that, the performance extreme is also a bad decision, because if you actually wanted to make the most optimal thing that ever existed in the history of humankind for this particular platform, you would never finish it, right? Because there's always more optimization to do. So what we're looking for all the time, right, is the right balance. We're looking for the right balance of something we can achieve that we will actually have time to do in the course of the project, and that efficiency that actually causes it to be a good, high-quality product that when you run it, you feel good, it's reliable, it's fast, it's not wasting your time, it's not stuttery, it's not ugly, and so on, right? And so push buffers allow you to have a kind of nice balance there, in my opinion. It allows you to insert this sort of this thought, if you will, this thinking, in between the output target and the game that allows you to do optimizations in a nice space. So you could almost think of it as an IR, an intermediate representation, for your render language. Like it's sort of like a compiler has an intermediate step. And this thing should be designed basically for two purposes. It should be designed to allow the game to quickly, this should be a fast pipe here, so it should be quickly describe what it needs to describe in terms of rendering, and also minimally, right? We want to minimize, because again, we want that balance. We don't want to be super piggy. We don't want to put the pig hat on. I've got it here, but we don't want to put it on. We also want to be relatively minimal. We don't want the game to be spamming giant stuff into this push buffer every frame that's going to cause a performance problem for us. So we want it to be able to quickly and concisely represent the things that it needs to represent in order for rendering to occur. And then what we want to do is write good, highly optimized ways of taking this push buffer and turning it into one of our output targets. Either OpenGL calls, Direct3D calls, some other API, I don't know, a console if we ported to one, or our software renderer, which will be the first thing that we do, which will be written, presumably we'll do the SSE2 one because that'll run everywhere, so everyone will be able to follow along at home. And let's be honest, I don't even know if I have AVX. I don't think I do. I don't know if I have AVX in this box. It probably doesn't have it. I'm not sure. So anyway, that's what we're going to be doing. We started doing the push buffer stuff, and so I'm going to kind of here, I'm not going to spend much time, maybe 3 more minutes talking on the Blackboard, and then we'll spend the 40 minutes just kind of working with the push buffer and showing how we want that stuff to work, and kind of getting things set up for a little more of our renderer stuff to happen. Okay. So that push buffer, that's how this is going to work. We've already kind of done the work on Friday of getting a sort of semblance of this started. We have these output targets here. We don't really know anything about them. I happen to know a bunch about OpenGL and stuff like that. I know something about software renderers as well. So, I'm at an advantage here, certainly compared to people at home who maybe have no experience with this before. But in general, I'm trying to take the tack as if I don't really know much about it, because there are ones that I have no experience with. I don't have I don't even have a machine that runs Mantle right now, I don't think, and so on. So I'm still thinking of it in terms of like, yeah, there's output targets here, and we don't necessarily know everything about the output targets we're targeting. We don't even necessarily know what they all are, because by the time the game ships, we could end up with a surprise. The Chronoscoop could ship Vulkan, right? And we want to target it. We don't know anything about Vulkan, right? I've never even seen the spec for Vulkan. So again, what we're trying to do here is set ourselves up for success so that we can rapidly adapt to new targets and get reasonable efficiency out of those targets without having to rewrite our whole game, because that would be bad. Okay. So that's what we're trying to do. And then our push buffer is essentially going to get handed in our first phase. We're going to be doing our software target here. So our software target is going to essentially be doing what I would call, I kind of just decided this is what we're doing at least to start, GPU rendering. Or I should say maybe more specifically, GPU-esque rendering, right? And what that means is we are going to be writing a renderer that works the way a GPU would roughly. Now, obviously, it's not exactly like a GPU would work, but it's similar. And why are we doing that? The answer is because there's really no reason for us to ship a software renderer, right? We literally, there's no point in shipping a software render these days. It just doesn't make any sense, right? But at the same time, knowing how a GPU works, I mean, a GPU is just CPU. It's just like an Intel processor at the end of the day. It just has a few different trade-offs in there, but it's very, very similar. It's just kind of purpose-built for a specific task instead of a more general task, right? What's very important to know when you're working with GPUs is how they actually function. And so what I think is the most interesting thing for us to do with our software renderer, because I do want to show you how that whole pipeline works, is to write something that works essentially the way the GPU actually does work. What that means is we're going to be a little slower. So we'll be a little slower than if we didn't, right? Than if we were, 100% CPU focused. Okay. So we'll be a little slower than that because we won't take any shortcuts that would only be, that would structure the algorithms so that they run specifically for a CPU and what a CPU wants to do, right? We won't do that. But what it does mean is that we'll get like basically all the insight out of it, right? So we're going to maximize the degree to which we get insight into how games are actually running today, because that's the biggest takeaway, I think, and it's the thing that's the most immediately applicable to everything. So when we walk away from this, we'll say, okay, we kind of now have seen how everything in a GPU works roughly, at least the parts that we care about. And we have some idea of why shaders look the way they do, why they have the performance characteristics that they do, that sort of thing, right? And so what that means in practice, really the primary thing that implies, is that we are not going to be doing a scanline renderer, right? And so there's kinds of renderers, there's two kind of ways you could look at a renderer working, and they look like this, right? So here's my pixel grid. I know it ain't great, right? Here's my pixel grid again. Okay. So one way to do it is to say, all right, if I'm going to draw something like a triangle, right, and I've got that triangle here, there it is. One way to draw a triangle would be to say, let's figure out what sort of scan lines the triangle touches or something, right? And I'm going to then go through them and figure out what the span is of this triangle on every scan line, right? Basically, which pixels it spans, if that makes sense. Okay. That one it wouldn't actually cover, so it'd probably be here, right? Something like that. So you basically figure out which pixels it touches by doing it in an iterative scheme where you first figure out how much to step each edge as you go down, and you start with a span that's however wide it is, and you exactly rasterize the rows you need to rasterize, right? That's the old school way of making a software rasterizer. That's the way software rasterizers typically worked back in the Pentium days when they were the common thing that games shipped on. We're not going to do that. Even if that turned out to be the faster way to do it today, we're not going to do it that way. That doesn't mean it would be, but that we're not going to. The way we're actually going to do things is by actually, it's an implicit surface rasterizer, essentially, instead of explicit. You could think of this as an explicit rasterizer, right? And this is an implicit rasterizer. Instead of walking the pixels that we want to fill, what we're going to do instead is only get a rough approximation of what they would be on some boundary. And so let's say that boundary, because this is probably what we actually will use, is 16 pixels in a square. So it's a 4 by 4, right? It's 4 this way and 4 this way. And what we will do is we will try to determine which 4 by 4s it might touch on the screen, right? So instead of being explicit, we're doing some binning to figure out roughly what 4 by 4s it touches, and then we will evaluate every pixel in the 4 by 4, regardless of whether the triangle touches it or not. So if the triangle actually passes through it like this, and these pixels are never touched, and similarly it passes through it like this, and these pixels are never touched, it doesn't matter. We will actually compute the results for all of these pixels, and then we will simply mask away these pixels here and fill only these, right? Now there's a lot of reasons for doing it this way. Hopefully a fair number of them will become clearer to you as we actually implement it. I don't want to kind of go into them all now, but this is how GPUs work nowadays. They do this sort of a scheme. And so that is what we will be focusing on, which means that our renderer will look something like push buffer here, right? Here is the push buffer. Goes into some kind of a binning phase, right? Which is going to figure out where on the screen stuff lives of all of our triangles, right? It is then going to go into 4x4 selection, right? So it's going to pick what 4x4s need to get filled for any given triangle, or whatever the primitive is. This is for primitives here now, right? Right. And then we're going to have a 4x4, basically, I don't know what you want to call this. It might be weird to call it a rasterizer, but I'll call it a rasterizer. But basically something that actually does the calculation for the 4x4, right? And this will be written essentially so that on SSE, right, on SSE2, which will be our minimum target, that's 4 wide, which means it calculates 4 at a time. That means we will be doing 4 times basically the pipeline for SSE2. We'll be doing 2 times the pipeline for AVX because that's 8 wide. And we'll be I'll be honest, I don't remember their naming schemes. And 1 times the new AVX 512. I think it was called AVX 256 or something. I don't even know. Intel's naming schemes mystify me. I never know what I'm talking about. I know the instructions I'm thinking of, but that's it. So there's another one that's 16 wide. I think that's coming out in Skylake. So like the end of this year or sometime, this will be a thing that's on desktops. And so this SIMD pipeline will actually be able to do the entire 4x4 rasterization in like just, a list of instructions that looks like it's just operating on 1 pixel is actually doing the whole 16 by 16, right? So this will be quad pumped, this will be double pumped, and this will be single pumped, and that's roughly what we'll do. And this right here is essentially where our shaders will come in, right? This will be where we write sort of what we want to happen per pixel. And we will have basically that working in a way that allows us to run it at one of these granularities depending on the platform. I don't know if we'll ever do an implementation for AVX 256 or 512s ourselves actually, but what we will do is set up the code so that it essentially is already working as if it was AVX 512 and it just quad pumps the SSE2 part of it. That's probably how we'll set it up. All right. So that's what we're building, okay? And we're starting with this part, and we'll maybe sort of cautiously start to work our way down until we get to this. And right now we're working primarily with rectangles, right? And because we're a sprite engine, I'm thinking that probably we will be exclusively rectangles. Meaning, although we may think about things in terms of triangles on a rare occasion, I'm trying to think in my head if we ever actually want an actual triangle, and we probably don't, which means we can save a lot of fussing through the pipeline by just dealing with rectangles explicitly. And that actually includes this, because as you will see when we get there, it is actually almost the same cost to fill rectangles as it is to fill triangles, so we will essentially save ourselves half the work by just filling rectangles explicitly, if that makes sense. And hopefully it does make sense to you. Okay, hopefully we're all on the same page. We've got a good 30 minutes left here, so I'm going to stop the Blackboard session because we can come back to it later when we start to get into some of these things in more detail. So right now I just want to take the rest of this time to start looking at our push buffer and start thinking about how to make this into something that's nice and clean for the game side to use, and maybe extend its feature set a little bit, even though we have no backing for it, to allow it to express the things that we're going to want to express. And when I say that, I'm kind of explicitly talking about things like scaling and rotation, which we have not been doing because we want to be able to push those through the pipeline so that they can actually be used in the subsequent stages, right? And right now, the game has no way of even asking for scaling or rotation, so it wouldn't matter if we had a back end of the renderer that could actually handle it. It doesn't matter. The game can't ask for it. So that's another thing that we kind of want to look at. So let's just start, get our feet wet. It's a Monday. I don't expect much from myself, let alone you guys on a Monday. You know, we're all sleepy. So I don't blame you. I don't blame you. I'm tired too. I know you've been out partying. That's just how it goes. It's totally fine. Let's not get hung up on it, okay? Let's just take it easy. So what I'm going to do is I'm going to start pulling some of this stuff out. We've got some stuff here: draw rectangle outline, draw bitmap, draw matte, right? You can see it all there. I'm going to go ahead and say that stuff is coming in here, so we can look at it all, just, you know, kind of have it all in one place. Recompile, make sure nothing's broken there. We didn't break anything. Oops, did I actually? No, I didn't. Dev env. There we go. You know what? I type msdev so often because at work I have a batch file that will do that for me. I'm wondering if I should just go ahead and make msdev.bat here in the mist directory and just say, you know what? Devenv. There you go. So let's see if that works now. Be gone, ye. msdev. Lovely. All right. So that was what it used to be called. They changed the executable to devenv. Nobody knows why. They just did. I guess they wanted to make sure everyone had to learn a new thing to type. And really, it was really worth it because now everyone knows it's devenv, not msdev. So good decision, guys. Anyway, let's go ahead and take a look at where we're at just to make sure everything's fine. It looks fine to me. We're just kind of in doing that cache filling there, so that's totally fine. I don't think there's really anything that we need to worry about here. It looks like everything was left in a workable state. So let's go ahead and start playing with this. Okay. Here we are in handmade render group.cpp. That's got our functions in it. Here we are in H. This has the stuff that we were working with. So we have a render group here. And you know what? We've got piece count. It's still in there, but I don't think we use that anymore. Why am I'm misaligned? Let's rotate that over there. There we go. So piece count is there. I'm going to get rid of that because I don't think we need that for anything. I don't think it actually is used. So I'm just going to vaporize it and get rid of it. There we go. And so what I'd like to do now is go ahead and say, well, let's look at adding multiple types of commands in here, because that's something we're definitely going to want to do. We're going to need something that allows us to kind of interleave commands or do sort of more fancy stuff with the commands that end up in this push buffer. So I'm going to try to expand things to that effect. So first of all, let's make this a push buffer entry, or maybe I should say it will be a render group entry. That might be a little bit smarter because, hey, it's a push buffer is kind of the implementation of it. It's not what it actually is, so that's fine. And so that way I can sort of change that sort of name there, which doesn't make sense. Entity visible piece is not what it actually is. So I'm going to replace entity visible piece with render group entry so that we can kind of have that taken care of. There we go. And same thing here. Just replace that anywhere that exists. Where else we got it? We got it here. Okay, so this is another thing too. I'm going to pull this out again into that render group, and there's really, this is strictly just for my own personal benefit of being able to look at things in one place. This is an organizational thing. It has nothing to do with the code. It's purely organizational. So I'm going to call this render push buffer or something, or render group. Render group to output. I don't know, something like that. And then I'm just going to go ahead and say that all the stuff that was happening in there, that's going to happen in here. And we will pass, now we will see what it actually is that we need to pass to make that work. Obviously, we're going to need the render group itself. That's, thing one. But then we're going to need some other stuff like the output buffer and things like that. So let's see. So screen center X, screen center Y, those can be determined from the buffer itself. Let's see what else we got here. Meters to pixels, that obviously is something that we can do directly off the render group because we were storing that, although that's probably something that we'll do in a slightly different way a little bit further down, but that's, yeah, a little bit further along in the process, if you will. But there we go, render group. Screen center we'll solve in a second, and draw buffer, same thing. All right, so basically all we need here is that draw buffer. So let's go ahead and grab that draw buffer out of things. It's just a loaded bitmap, right? And that's the target that we're drawing to. So we're going to go ahead and pass that as well, right? That's sort of the target. We'll call that the output target for now. So that output target is this bitmap. and the bitmap is going to, I think, give us everything else we need, because that's what we're drawing to there, those output targets. And then that screen center we can compute pretty trivially by just doing it off of the output target, right? So there's the output target again, output target. Let's take a look if there's anything else that needs to happen. I don't think there is. So this is our draw buffer, and this is also our render group. Get past here. And now we should be, again, nothing should be changed. We should see exactly the same stuff. And again, this is just a simple programming step. You'll notice, and I want to keep emphasizing this. I know you guys have heard a bunch of times, so I really can't emphasize it enough. You'll notice that no design work is happening here. The design is happening organically, and that's really, really important to understand. Like, basically, I have some stuff that I want to do, and I'm just pulling things out and letting what was already in place as a structural set of requirements for the code guide what lives where and who does what when, right? I'm making these sort of incremental steps. That's a really important skill to learn. It's a really important skill to practice, because it's what keeps you out of the bad habit of over-designing, overthinking, not getting anything done, sitting there drawing things, class diagrams or things like this, which are all just basically totally useless. Like, you really want to focus on write the code that works, and then start pulling it up and cleaning it up and making it into nicer pieces using those compression steps that just kind of like pull things out, make them simpler, pull things out, make them simpler, that sort of leveraging. That's the way to do it. It works really well. You've seen it work a bunch of times really well on the stream, and it's going to keep working well for us. So I really want to emphasize it's really the best way to go. If you take anything else away from Handmade Hero, please take that away. It's a really valuable programming thing I wish I'd known a long, long, long time ago. And in some sense, it's something everyone starts out doing. Like, I used to do it instinctively until a bunch of C++ nonsense, books and stuff, and people essentially taught me out of it by telling me that this was better code was the other way. They're wrong. It's not. So please, follow your instincts because your instincts are good. Don't follow the books because the books are lousy. Okay. So again, we're in a good place here. We've got our render group to output working. And so now what I want to do is introduce a different type of command so that when we're going through the push buffer, we can have commands that are kind of interleaved. Now, again, this is somewhat inefficient because we have different commands. We have to look at each one to see what we need to do. But remember, that's why we're focusing on trying to be concise with these commands so that we're not constantly, like, we don't want to have like triangle or rectangle be necessarily the, how should I put this? We don't want anything that isn't relatively expensive to render to be in the push buffer as a single item, if that makes sense. Like, we don't want to fill the like, let's say particle. Let's say we had particle effects. So tons of rectangles that are drawn with the same texture. We wouldn't want to push each particle into the push buffer because we'd have to keep deciding as each one goes. We have to say, what is this? Oh, it's a particle. Call some particle code, right? So what we want to do is aggregate those things up to the point as far as we can, basically, right? And so something like a bitmap we can actually probably make that one entry because that's going to require switching what texture we're using potentially and things like that. So we can think about that as being appropriate for a push buffer because maybe there's 100, 1,000 of those on the screen. That's not that big of a deal. But things where there's going to be like 10,000, 100,000 of them, it's not an option to put them in the push buffer individually because all of that testing to see what they are will kill us. So we have to be careful what we do. We'll start right now with just doing something very basic, but keep that in mind that we're going to have to do some things there that allow us to that will prevent that switching overhead from becoming any kind of dominant factor. We don't have to think about it all the time, but we have to think about it a little, is I guess the way they would say it. So when we grab out an entry here, right, and I'm going to change the word piece to the word entry so that it's a little more clear what that is there. So when we grab out one of these and we're looking to see what we want to do with it, right? When I do that, what I want to do is I want to say, okay, let's see what type it actually is. So when we grab an entry, we're actually going to see what type it is. And then based on what type it is, we're actually going to do different stuff, right? So we might have a render group entry that's going to be a clear, right? Oops, sorry. It's going to be a clear. We might have a render group entry, because I spoke of that one before, that's going to be like a rectangle, which is, you know, like I was saying before, that we kind of know is where a lot of our sprite building is going to come. And then we'll have other stuff here, right? Now, we don't know what that stuff is going to be, but we're going to handle basically everything that we possibly, that goes through there. We want to make sure that we handle it. So what I'm going to do here is introduce another one of our invalid code path things, which is invalid default case. And what invalid default case is it's just a macro that lets us know that the default case in our switch statement is not allowed to ever happen, right? It's just not. And so if it ever does, we want to assert, because basically the only things that should ever get pushed on here are things that we can handle. And if there's something that we don't want to handle for some reason, we should add a case for it and note we're not doing anything for that case. We're just not handling that thing. Like, let's say it was something that was only applicable to OpenGL or something like that, right? Okay. And so then what I'm going to do further is I'm going to say, all right, that base address, right, is actually going to go up, whatever we're advancing by, is actually going to go up by a different value depending on what's in here, right? So they're going to kind of be compressed. Now, that may not be the fastest option at the end of the day, but I want to make sure we support it, so I'm going to do that for now. We will see what we want to do at the end of the day for it, because there's other stuff we could do there. We can do it this way. The other way we can do it is by having some pointer chasing happening there. Again, I'm not sure which one of those we want to do, so we will kind of leave it open, and we'll see. We'll sort of see what happens when we get to it. All right, so when we do this, what we want to do now is say we've got our render group entry. So let's say render entry clear is a thing that we have, and we're just going to cast, right? We're gonna basically cast whatever the entry was to be the thing that we know that it actually is now after that type. This is basically a discriminated union, if you will. And then we're going to have a rectangle. That's another option here. And that's going to be done like this, where we have render entry rectangle, like so. And then we're going to act on those. And so what we want to do here, you know what I could do too, is I could just actually call this entry as well, like so. And actually make this be typeless entry or something like that. So when we know that's type, we turn it into entry. So then at the end, we will take whatever the size of the entry actually is, right? And we will advance by that thing, like so. So there we go. Okay. So now if we have these two, now instead of making render group entry be that thing, I'm actually going to make it so that there's two types. There's a render entry clear and a render entry rectangle. And right now, rectangle, we know what that looks like for now, at least. It looks like this. And then we've got a rectangle entry clear that is a different one, and that's going to be some other thing. Presumably, what render entry clear will be was just an RGBA. That's whatever we want to do our clear to, right? And then, of course, everything needs essentially one of these at the top of it, like so. We'll call that, well, we can actually call that the header, I suppose, like so on. And in fact, I could call this render group entry header, which might be a little bit clearer. I could also call it typeless render group entity. I don't know. It's not worth thinking about too much. So we'll just leave it at that. And so we're going to have an enum here, which is going to be the type. This is going to be the render group entry type. And the types are going to be the two kinds that I have, right? So I've got clear, I've got rectangle, okay? And so what I'm going to do in here is in that header, I'm going to have the type there. I'm going to have in addition to the type, wait, there was something else that I wanted to have. What was it? Oh, maybe there wasn't. Now that I'm thinking about it, did I misspeak? Do we only need the header? For some reason, I was thinking in my head just moments ago, I'm like, well, we'll put the type in there, and then we'll put something else. And then for some reason, I'm not thinking of anything. So it may literally just be the type. That may be the only thing we actually need. All right, I take it back. Take it back. Maybe it's a Monday and I just forgot what it was, and in a minute I'm going to be like, oh yeah, we need that thing. But there we go. All right, so what you can see, what I've done here, right, is I've essentially made what's called a discriminated union. All right, and I'll put that up here. So I'll just say, okay, render group entry is a discriminated union, right? And essentially what a discriminated union is, and furthermore, it's a, you might call it an efficient discriminated union, or a memory efficient discriminated union, right? Maybe a compact discriminated union. So union, as you know, is something we've used before in actual C, where we do like union, and we say, okay, we've got a union, it's got the render group entry header, I'm sorry, it's got the render group entry clear, it's the clear, we've got the render group entry rectangle or whatever. Sorry, like so. Rectangle, right? And what that does is that makes it so that the size of each of these things is whatever the largest one is. So they'll all fit. But what I want to do, and I should say, that's a regular union. A discriminated union, right, is one that stores what type it is. It discriminates, essentially, is what there's a type field that discriminates among the possible types that it is. So that's called a discriminated union, typically. Probably from category theory. I don't actually know where that term comes from. And furthermore, what I'm doing is I'm saying I'm going to actually compact these down so that instead of using like the largest size possible, so that I know that they all fit, and not having to, and I can always advance by the same size every time, like base address would always be plus equals the size of whatever the whole union size is. I'm actually going to say, I'm going to look at, since I'm already looking at what the type is, I'm going to advance by whatever I know its size to be. And there's actually a reason that I'm doing that. It's a little forward looking, but it's basically so that we can push arbitrarily sized stuff on the push buffer. And I think that you will agree with me when we get to the end of this that that turns out to be a really handy trick. But we haven't gotten there yet, so no need to really go into it now. Anyway, so essentially what we're doing here is we're making one of those unions. And I guess, like I said, maybe we really don't need that header. I don't know. I'll leave it on there for now, but it might be that we only need the type. So with that in mind, we now have the ability to sort of walk through these however we want to and process them differently. So in the case where we get a clear, we can actually do the clearing operation here. In the case where we get a rectangle, we can do the rectangle operation. Now we know what the rectangle operation is. It's this, right? But you can see this already had a discriminated operation in it. It was looking to see whether it had a bitmap or just a regular rectangle. So our next step after we get this working with the clear is basically going to be, let's pull those two out. So now we have the concept of two different types of rectangles. We can also add rectangle outlines in here, right? So now that we have types, we can start to kind of go nuts with having as many different sorts of things as we have render operations, which is exactly what I want. So let's keep going with this. Let me go ahead and compile. So what we have to do now is say that push piece. Push piece is actually doing something slightly different. We've got push render element. Again, I kind of set us up for success. This is a little bit of the just the experience talking. I kind of know roughly how these things go, so I'm not having to go through all the steps I would have to go to determine what a good architecture for a push buffer is. I kind of know one that I like that works. But it's not that much different if you didn't know. You just have to go through more iterations of trying things out. But you'd be programming in roughly the same way. You just wouldn't have that benefit of the look ahead that you do when you've done it before. And it's hard, and there's nothing you can do about that. That's just experience. And the more experience you have, the easier it becomes because you can make better decisions, right? So anyway, what I want to do here is say when we push a render element, we're now going to push not only the size of the render element, we're also going to push the type of the render element. And you know what I should do here? I should actually do this here. I'm going to do even yet another trick. This is the full ridiculousness of the world. This is a real ridiculous trick. I'm just going to show it to you because why not, right? So what I'm going to do here is I'm going to do a little trick, which is like, we'll prepend something to the type name itself to make the identifier. So our types in our enum are the same as our structures, only with this prepended to them, okay? And then what I'm going to do is I'm going to define push render element to be a macro. The macro is going to take the group, and it's going to take the type to push on. Okay, makes sense? And then what that's going to do is that's going to call our actual function. It's going to pass the group straight through. It's going to take the size of whatever that type is and pass that, but then it's also going to go ahead and take that render group entry type prefix and it's going to paste it on to the type name. Okay? You see how I'm doing that? And what that allows us to do is that allows us to make a nice type safe way without having to pull in crazy templates, without having to doing any nonsense. There's no fussiness there. Oh, and to boot, I'll cast it for it there so we know it's the same. So now we know we're getting back the right type, and we also know that we're setting the type field to the correct thing in that step, right? So now when we call push render element, all we have to do is say which one we actually wanted to have, right? In this case, we wanted to get a rectangle out of this. And once we've done that, we know that everything else will be taken care of for us. So in here, we've got that type we're passing in. So when we get the push buffer result out, we want to go ahead and call that at least the header, right? If that makes sense. You can think of this as returning a header because we know that no matter what we allocate, it will have that sort of header on it, if that makes sense. Although I suppose we could go one level deeper and allow things that don't have that header on it to be inserted there. That's something we might decide to do, and if that was the case, we'll put a push size above this one level deeper. Again, not something we have to worry about right now. So when we do that, when we push a render element on, and we do this result here, when we grab the result, again, we're going to be casting it to this just so we can sort of access it, and then we're going to say, all right, the type equals whatever the type is. If we want to support running out of space, it's actually very easy. We just do one if at the head end of things to make sure that we actually got one. Otherwise, it's discarded. We essentially forget about it. And that's really all we need to do, if that makes sense. It's really pretty straightforward. Oops, that's the underscored one there. All right, so, oops, what happened there? Oh, sorry. Got to have a paste operator in the right place there. There we go. My bad. All right, so grabbing out the header, right? We'll just do it like this. Render group entry header, right? That gets us our header. And then we're just going to cast the header to whichever one we want, like so. We change the names of these types to be like this. So there they are, like so. And again, oops, like so. So now we've got those straightened out. And I believe things probably will still run just fine. They do. And so all we've done now is just make things a little more convenient for ourselves, again, to put ourselves in a more reasonable position. So let's go ahead and do that next step. So let's do one where we've got sort of bitmap, which is our old call, and rectangle, which is just like a solid rectangle, right? Let's pull those out into two separate cases. So we've got these two cases here. I'm going to pull those out into two separate cases. I've got one which is render bitmap. I've got one which is render rectangle, and we're going to look at these two together. So what we're going to do is say assert that this one has a bitmap and draw the bitmap like so. The other one is going to essentially just draw it as if it was a rectangle. And now when we look at these two things, we're going to have two separate versions here. We're going to have the bitmap version, right? And then a rectangle version, which doesn't have the bitmap at all. Okay? Those are the two ones that we're going to have. And then we're going to compile that, right? Now, when we push this on, do a push piece call, we've sort of got two different pushes to do now. We've got the push piece call that pushes on a bitmap, and we've got the push piece call that pushes on a rectangle, right? And these right here are the ones that do rectangle pushes, this one and this one. And then we've got the bitmap one, which is here. So what I'm going to do is I'm going to go ahead and sort of, I'm going to take this one step at a time. We have a little more stuff that we want to do to it, but I'm going to take this one step at a time. So first what I'm going to do is I'm going to still call the push piece function for the bitmap like that. And it's going to get called here, as you can see. Oops, rectangle entry bitmap, so. And inside, why does that not have, what did I, oh, this is bitmap. There we go. So that should work, except for now we should hit an assertion. The assertion we should hit is as soon as we try to draw a solid rectangle and that entry bitmap is not filled in, right? And you can see what that's from. So now what we have to do is make it so that when we actually call that one in particular, we will actually push a rectangle on, not something else. So let's take a look at how when that push rect ever actually gets used, if that makes sense. I can't actually see because the 5-minute warning is blocking me at the moment, which is not what I was hoping for. But let's take a look at that push rect. So when we draw hit points, we've got draw stairwell. We've got a couple of these here. We've also got sort of any space that was drawing rectangle outlines. So when that gets called, I'm just going to duplicate this code for the time being. Duplicate it like so. And then we will take a look at what we can do to make it so that that's not being duplicated in that way. So there goes the bitmap, right? Off we go. And then we have that align, which is not actually in there for the rectangles. Okay. So I think that should do it for our rectangles. And they are still being drawn. As you can see, there's our rectangles. They're underneath the guy, as we would expect. So that's fine. But we've got a bit of duplicated code there, and there's some stuff that we want to start to take a look at in terms of, again, pulling that out. And like you can see all of this stuff here kind of being common, right? And similarly, when we do the push, we're getting a lot of sort of duplicated code there, right? So what I'd like to do is I'd like to kind of compress that down into something a little more sort of usable for the time being, at least, even if we don't stick with it. What I'd like to do is say, okay, there's going to be a shared piece here. There's going to be sort of a render entity basis or something like this, for lack of a better term, where that's actually kind of gonna have the basis, this offset, the offset z, the zc, that stuff that really is about positioning it relative to an entity, right? I'm going to pull that stuff out because it's really sort of a positioning scheme that has very little to do with what the shape is that you're actually drawing, right? Like none of this has anything to do with the shape that you're actually drawing, like the bitmap or whatever, or the rectangle. It's much more specific. Furthermore, we could also compress these RGBAs down to V4s, which does seem like a good idea as well. So, you know, in fact, I could even pull the dimension out there. We'll see if that's a good idea. It might not be a good idea, but we'll see if it's a good idea. All right, so let's go ahead and do that. Then these guys basically get a new notion of basis, and their basis is actually doubly indirected, right? So they've got an entity basis, like so. It's not actually indirected because it's built straight in, but you get the idea, right? So there we go. Now, what else do I want to do here? What else do I want to do? Okay, so then I can take this stuff and go, all right, all I really ever got out of this stuff was that center bit, right? All I ever got out of it was just center. That's it, really. So I just need to be able to call I just need to be able to call something that will take one of these entity bases and do all these computations for me, right? So what I want to do is just introduce a function where you basically, you know, you do something like compute entity offset or compute basis offset. And you notice we've got a little weirdness here. The half dim's a little odd because what is entry A? That's the alpha. Why does this guy never use the dimension of the bitmap? Oh, because it's baked. It's actually baked in. Okay, so that's actually something we should take care of as well. I probably did this a little bit too soon. All right, so let's do this. Let's do this in 2 minutes. I might go about 5 minutes over. We started a little bit late, so I don't feel too bad about it. So what I want to do is when we do a push rect call, I don't know if you can see here. Where is that push rect call? Oh, you know what? That's because I moved it out. So when we do a push rect call, Did I not pull it out? Where is pushRect? Oh, it's in the H file. That's right. So when we do a pushRect call, and these I could probably move out of the H file now as well. They don't really need to be in the H file. So you know what? They probably shouldn't be. Let's get them out of there. Let's put them in here. There we go. All right. So if I do my pushRect call, if I take a look at my pushRect call, right? Really, I think what should have happened is we should try to do the offset. We should bake in whatever that was that we were doing that made it different from computing the entity offsets from everything else, right? So in here, we're doing this thing where we take the center and we offset it. We really want to make it so that this is just sort of this coordination point, and they both draw from the same one. So instead of doing a center minus half dim and a center plus half dim, what we want to do is kind of bake that out over here, I think. That seems like a smarter thing to do to me, if that makes sense. So what I'd like to do is I'd like to suggest that we go ahead and say, well, whatever the meters to pixels was, right? We're going to go ahead and compute that half dim here, right? So the dim will just come out that way. And then what we're going to do, do we actually, when we do draw a rectangle, center plus half dim, center minus half dim? Yeah, so this will just turn into something which instead of using the half dim, actually uses the full dim, if that makes sense, like so. And I'm trying to think if there's anything else. Do we actually need, where does dim actually get used in here? Because I don't actually know. So dim, entry bitmap. So dim only really gets used for the rectangles, right? Like so. And so really, yeah, really what we can do is we can totally sort of slap this down into something a lot more sensible. So we'll do the meters to pixels here to do our dim call, which we'll actually have here as well. And again, we'll start moving things around a bit here. So we'll do it that way. So we'll do basically our p plus empty dim, and we'll start here. So that is more what I want to see, right? p.x, p.y, like that. This is more what I want to see, so they're all based off the same point, essentially. So now we've sort of gotten rid of the notion that the other one's different. And then this half dim here, when we compute our offset, we'll just subtract that half dim away. Or of course, I guess we have to do it the two different ways because of our whole y flipping thing. So we have to do something where we do half dim.y and our half dim.x. We want to basically subtract the half dim x and add the half dim y, I believe, right? Because of the way that we're flipping things. I don't actually know if that's true. I don't remember. What was the way that we were doing it here? Let me take a quick look, because I don't remember. I want to make sure we're basically doing it exactly the same way that we were before. So it was just minus and plus. That's all it was. All right. There we go. Sorry, like I said, Monday, it's a bit difficult. So in here, I guess we've already done anything that we would have needed to do in that sense. So it's just minus and plus. So all right, I'm going to leave it that way and say that that was the way that it was going to work for now. Yeah, let's go ahead and assume that that's correct for now. We'll debug it in a second. All right, so if I've got that, I don't need the v2 there anymore. I'm going to take a look now at just pulling out that computation. And all that's going to do is like compute some kind of an entity base for us. It's going to take one of these guys, the render entity basis, right? It's going to be like get render entity basis p or something like this. It's going to take one of these, which was what, entity basis. And in both cases, we'll compute that, right, like so. And then what we'll do is it'll just do this, right? So it'll do literally this chunk of code right here, and just in a duplicated way, presumably. And so that'll return a v2, I guess is what that'll do. And let's see, render entity basis p. It'll take one of these, oops, render entity basis, like so. And I guess I'll call that entity basis, like so. And we will also pass it the render group, like that. And we will, just go ahead and do that there. We will return the value that computes, and we just need to go ahead and change entry to entity basis I think that's mostly all we actually need to do there. And then vaporize this stuff, make sure it's all kosher. Okay. Okay, so we need that screen center X, screen center Y. That's got to be in there, so let's go ahead and pass that screen center, like so. And then in here, we will go ahead and pass render group, render group, and screen center. Now, screen center is probably actually also known all throughout the pipeline, so we could also choose to sort of bake that in a little bit further, but that's something we'll get to a little bit later. We also need to take the address of these entity bases here, like so. And these are v2s, not v3s. All right, so our entry, it says we don't have a dim. That is a mistake. And this was actually supposed to be pulled out to just be in the rectangle, because I realized it was only in the rectangle there while we were doing that. So off we go. All right, so we've got an entity basis now. We've just got to fill it out. Again, here are the members of that, right? And pieces no longer have dims at all, right? If I'm not mistaken, those are just gone. And then we also have in here our render group. I guess it's just called group in here. Should probably call it the same thing everywhere. But sometimes, again, when I'm talking on the stream, it's kind of hard for me a lot of times to concentrate as fully on the code, so the code doesn't come out as good as it would otherwise. I apologize for that. I do the best I can. So, all right. Probably made some mistakes there, but let's see where we're at. All right, so I think we're in good shape. That all looks correct. So I guess we can stop for now. We're only a little bit over, so we can go ahead to that Q&A. We made some decent headway there. We're going to want to keep pushing forwards on this, pulling things out, making this a little bit cleaner. You can sort of see it starting to clean up a little bit, and it will continue to get cleaner over the course of the week until we've got a really, really nice push buffer system that specs everything out that we want, and then we can sort of focus our attention to actually how we turn those into more efficient drawing calls and add some of those features that we need, like rotation and scaling, which is kind of where the more meaty, pixel, finicky work happens. All right. Q colon before the questions, please. If you could just put Q colon before your questions so I can see them. And the other thing that I would like to do is, again, if you're new to the stream, our post-stream questions are for programming, what we actually have been working on. So please keep your questions confined to that. If you want to just do general chatty questions or off-topic questions, I'm totally all for that, but we do those before the stream. So come back about 15 minutes before a scheduled start time and ask away. I'm happy to answer them there, but I just flat out skip most of the time questions that are not about the programming here in the post-stream, because I like to concentrate on the actual code, if that makes sense. Pseudonym 73, he's a very frequent viewer, I guess I'll say, of the show. He is sort of our resident math expert, it would seem. From most of the comments that he makes they're not the kinds of comments that somebody who doesn't know a lot of math would ever make. He says, warning, there may be lots of pre-stream questions today. So I guess I'm glad I warned against that. I don't know what that means exactly, but yeah. So I'm not sure. When you meet a bug in the game and are able to recreate it, will you get a bug line in the programming, or how does it work? I'm not sure what that question is asking exactly. But when you get a bug, typically there's two types of bugs. There's ones that are very easy to track down and you quickly know where they are, so you go find them and fix them. Other ones are much more complicated and you have to spend time creating situations that allow you to deduce what's going on, and then you can fix them. But I'm not sure what a bug line is, so sorry about that. Is it worth aligning render entries? So here's what I'll say. At the moment, no, probably not. And that is because all of our render entries will already be 8-byte aligned anyway, right? Because basically, you've got these, you sort of got these render entry things, and they're all going to have pointers in them, so they're all going to be 8-byte aligned. So you're pretty good to go. But when we start pushing things on that are more variably sized, we will probably align those. Because we don't want to probably leave things on odd byte boundaries or anything like that. Alignment past that, probably not, but I don't know. I mean, really the answer is we'd have to test it. You never know with alignment. Sometimes it benefits you, sometimes it hurts you. If you spend a lot of time padding things out for alignment, but that ends up taking more total space, you may find that your memory bandwidth or cache pollution or something becomes that eats up any gains you could have gotten from any sort of alignment win, right? What is Mantle? Mantle is AMD's direct hardware access, well, direct, not really direct, more direct graphics API for accessing their GPUs. Any recommendations of some reading about GPUs rendering rasterization except for a Google search? For once, when someone asks that question, because I get that sort of question a lot, like, do you have any good ideas for reading about blah? And I'm always have to be like, no, I don't know where this information is. I do, actually. I absolutely do. And what you want to do is go to Fabian's blog. When I grow up, I'll be an inventor. This one right here. Fabian's blog is Fabian Giesen. He works at RAD. He's like definitely one of the best programmers I know or have ever known, for that matter. And if he happens to have written a blog entry about something, much like I said, if Raymond Chen writes a blog entries about Windows programming, you probably want to read it. If Fabian writes an entry about programming, especially graphics or optimization, you really want to read it. And in this case, we are lucky enough that he has written one about the graphics pipeline. So what you can do is you can go in here, and there's a graphics pipeline one. I would highly recommend clicking on that. And if you can set aside some time for going through these, you can start here on part 1, and he will set you up for understanding a lot of the stuff that has to do with why graphics works the way it does, right? It's really great. It's going to be even probably more than, he knows more than I do about it, so it's going to cover probably even more than what we will cover. So if you can spend the time to dig into some of this and understand it, you will probably be a very happy camper. Now, regrettably, it is a 2011 trip through the graphics pipeline, which means that it is a little out of date, and graphics does sort of change over time, but to say the very least, it will certainly give you the perspective you would need to understand a graphics pipeline from 2015, because they don't change that much, and it will give you the right perspective so that you'll be able to read other stuff that tells you how it's been updated and understand what they're saying when they tell you that, right? So very, very, very important blog. Highly recommend reading it. And this series in particular, for the question you were asking, is definitely the one to read. I can't think of anything else that's even close, although there may be some that I'm just unaware of, but that's the one. And if you actually read and internalize all of this, you'll probably know more about the graphics pipeline than I do. I don't think I've read all of these at the level of detail that I probably should have. So I would highly recommend them. Why use pointers over references? There is no difference between those two things. Pointers are just a superset. Right? So the reason I use pointers instead of references is that pointers and references do exactly the same thing. There's no, especially when we're not using any C++ features really, we use a little bit of C++, but our coding style is very C-like. We don't use a lot of C++isms. A pointer and a reference both mean the same thing. There's no difference between the two of them in terms of what the CPU is going to do. It's not telling it to do anything differently. And so a pointer is a superset of a reference because a reference can't be assigned to something else. Right? A pointer can be changed to assign something else. A reference can't be, although my understanding is they changed that recently, I think. I want to say that the new C++ spec actually allows you to change what references point to or something. I don't even remember. It's kind of silly. So yeah, references, they don't do anything, so I don't use them. They're kind of a useless language feature, honestly. They don't actually do anything. So I don't use them because, why add complexity for no reason? You have to use pointers. You're going to use pointers because pointers are very important to do a bunch of things that you want to be able to do, like arithmetic. And references can't do those things, and so they're just kind of a weaker pointer. So I don't like to use them. About Mantle, were you aware AMD dropped development for it and put a lot of that manpower into helping push Vulkan? No, actually, I'm not aware of that yet. I mean, I was aware that they were trying to help with Vulkan and trying to make Mantle sort of be a basis for Vulkan and so on. I did know they were doing that, but I didn't know they were dropping support for Mantle yet. Are you sure? I mean, I don't follow AMD very closely. Sorry, AMD people, no offense. I just don't. So I had no idea. For all I knew, Vulkan's not a thing yet, right? So for all I knew, I assumed they were still going to do Mantle at some point, but maybe they're not. The push buffer is an abstraction layer relying on memory for communication instead of a bunch of functions, if I understand correctly. Is that how you prefer API design in general? The answer is yes. I do prefer API design to be memory-based, not function-based. And the reason for that is I feel like it's better spec'd, it's more flexible, it has a bunch of important aspects, things you can do for it, such as tracing, capture, and stuff like that. And so APIs that are based on functions tend to be hairy, they tend to be complex, they tend to be difficult to document, whereas APIs based on memory layout tend to be the opposite of all those things. So yeah, it's what I prefer. Certainly for anything like a renderer. There are other times when maybe APIs make more sense. Function-based APIs make more sense because you have kind of a sprawling concern. Like the whole game, for example, has pieces that have APIs in them, and you wouldn't want to turn those into memory APIs because it's going to be too complex for that. So I guess I should say I prefer that kind of API design when you have a problem that's straightforward, like rendering is, that has very well-defined ins and outs in that way. Any more questions about the code? Anyone? Anyone? Not seeing any. So I think we're close to wrapping up, I would say. Yeah? All right, well, I don't see any more code questions, so I guess we are done here. Yeah, seems good. I think that basically the push buffer stuff should be relatively clear. Again, no mystery here. We need it for two reasons. We need it, one, sort of to support that multi-target stuff. I like to use it to support the multi-target stuff, but also for the sorting and sort of organization of the things that are coming out of the game. So we're going to try and push towards that. One thing that we'll probably try to do relatively soon after we get some of these divisions in there a little bit more is we'll try to add that sorting in. And that'll actually fix a bug that we've had for a while, right? If you remember, our little dude here, he goes behind trees sometimes depending on the order in which the game happens to traverse those entities. So that will fix that bug for us, which is kind of nice. It's just nice to kind of have that taken care of for us, so that's good. So yeah, so I would say that we'll get like kind of a nice benefit out of doing that. And then soon after that, we'll probably get another benefit too, which is that our integer snapped coordinates, which kind of cause, you can see a little shimmering in the trees, they kind of have that sort of stopping pattern, which you see a lot in games nowadays. Actually, I've seen like a lot of 8-bit games or sort of demake style games having this kind of ugly jitter. We'll be fixing that pretty soon as well too, because now we'll have a real renderer that can deal with that stuff properly. It makes a big difference, and so we'll try to take care of that as well. So anyway, good stuff on the horizon. I'm excited to get the renderer taken care of as well. So let's go ahead and save our state here on the blackboard. We'll close down our compiler and our editor, and we will close down for the day. I'll double check to make sure there's any other questions. Let's see if there's anything else. Does not look like it. All right. So thank you everyone for joining me for another episode of Handmade Hero. It's been a pleasure coding with you as always. I am excited to do some renderer works. This is going to be a fun week, I think. It's I don't know. Getting stuff on the screen graphically is always fun, so tweaking with that, it's just, I don't know. It's a lot of fun. So anyway, I'm excited to do that. It just kind of emerged. It's just where the code was going, so we're going there. That's just how it's going to go. So I hope you'll join me tomorrow, again, 5 p.m. Pacific Daylight Time again. Hope to see you here on Twitch, same time, same place. If you would like to follow along with the source code, you can always pre-order on handmadehero.org, the game. If you pre-order the game, you get the source code during the whole development, so you can keep downloading it and playing with it and doing whatever you want right up till the day we ship. And if you want to do that, you can do that at handmadehero.org. You can also, if you want to support our video series, this educational series, you can subscribe to our Patreon. It's always much appreciated. We also have a forums page, and the forums page is where you can ask questions or find ports to Mac and Linux. There's also an episode guide on there that's pretty cool. Catch up with past episodes. There's a tweet bot that tweets the schedule, so if you want to know when the video series will be live, that's the place to go. So definitely check that out. And yeah, I hope you guys are going to have a good week, and I hope to see you back here tomorrow for some more renderer action. Take it easy, everyone.